Hey everyone, a massive, enthusiastic welcome to all our ninth grade geometry students tuning in from St. Paul American School, Clark. I am so pumped to be your guide for today's explainer because we've got a seriously fascinating mathematical puzzle to unpack together. The exact production title for our session is G9, Geometry, UO5, L10, Equivalent Trigonometric Expressions. By the end of our time together, you're going to be looking at triangles in a completely new, totally interconnected way.
Okay, let's dive into this. Here is our roadmap for today. We'll hit the lesson objective, move right into understanding equivalent expressions, tackle a worked example, do a quick misconception check, followed by a formative check, and then wrap the whole shebang up with a concept recap.
All right, Section 1, Lesson Objective.
Our goal today is pretty straightforward, but it's a real game changer. We need to understand how to write equivalent trigonometric expressions using complementary angles. Now, you might be wondering, what does that actually mean for us? Well, it means we're going to entirely demystify how complementary angles, the ones that add up to exactly 90 degrees, allow us to seamlessly translate back and forth between sine and cosine. It's honestly kind of like learning a secret geometric language.
Moving right along. Section 2. Understanding equivalent expressions. So, take a really close look at this right triangle. It's labeled ABC with our right angle sitting right down there at C. And notice the two acute angles? They're labeled with the Greek letters alpha and beta. Now think about this. The angles in any flat triangle absolutely must add up to 180 degrees. And since the right angle takes up exactly 90 of those degrees all by itself, what does that leave for alpha and beta to share? Exactly 90 degrees. That means alpha and beta are complementary angles. They will always add up to 90 degrees, no matter how much you stretch or shrink that triangle. Keep that locked in your mind for this next part.
And this brilliantly illustrates the real magic of trigonometry. Let's look at the ratios side by side. Imagine you're literally standing at angle A, which is alpha. If you want to find the sine, you look for the opposite side and put it over the hypotenuse, right? That gives you the ratio A over C. But what if you walk across the triangle and stand at angle B, beta? If you want to find the cosine of beta, you look for the adjacent side over the hypotenuse. And what is the adjacent side to beta? It's that exact same side, A. Boom. So the cosine of beta is also A over C. The sine of alpha and the cosine of beta share the exact same equivalent value. Mind-blowing, right?
Now, what's really cool here is the actual history of the word cosine. I know, sometimes trig vocabulary can feel super intimidating, but it really doesn't have to be. Get this, the prefix co in cosine literally stands for complementary. It is basically a built-in cheat code telling you that the cosine of an angle is simply the sine of its complementary angle. The answer is hiding right there in the name.
So let's formalize this rule. In math, we call these the cofunction identities. They prove that any two complementary angles can form equivalent expressions. If you know that alpha and beta add up to 90, then the sine of alpha strictly equals the cosine of beta. Written algebraically, using the angle theta, the sine of 90 degrees minus theta is exactly equal to the cosine of theta. Sine and cosine are perfectly mathematically linked by that 90-degree relationship.
Let's put this into practice. Section 3, a worked example. Let's see how this builds step by step with a real problem. Imagine you're given this equation. Sine of theta equals the cosine of 25. Step 1, just analyze what you're looking at. You have a sine expression set equal to a cosine expression. Okay, step 2 is where our new rule kicks in. For sine to equal cosine, those two angles, theta and 25 degrees, well, they absolutely must be complementary. They have to add up to 90. So, step 3 is just simple arithmetic. We calculate 90 minus 25, which gives us 65. Theta is exactly 65 degrees. Actually, it's a remarkably straightforward process once you spot that hidden connection.
Let's do a quick check. Section 4, misconception check. A very common pitfall, and honestly a totally understandable false assumption students make, is thinking that sine and cosine evaluate to completely random, unrelated values. They see two completely different buttons on the calculator and just assume they live in separate worlds. But as we've just proven, the verified truth is quite the opposite. The sine of an angle is strictly, perfectly equal to the cosine of its complementary angle. They aren't random at all. They're essentially two sides of the very same geometric coin.
Time to test it out. Section 5, formative check. Here's the question for you to ponder. For what exact angle measurement must sine and cosine have the very same value? I'm going to pause for just a couple of seconds here. I want you to really think about a number, an angle,
that acts as its own complement. So the crucial point is the answer is 45, because 45 plus 25 equals 90. 45 is its own complementary angle. Therefore, if you evaluate the sine of 45 degrees, it strictly and precisely equals the cosine of 45 degrees. If you type both into your calculator right now, you're going to get the exact same decimal value. How cool is that?
Wrapping it up now. Section 6, Concept Recap.
All right, let's do a high-energy recap of the required concepts we completely mastered today. First up, complementary angles always add up to 90 degrees. Second, the sine of an angle strictly equals the cosine of its complement. We proved this algebraically with the cofunction identity sine of theta equals cosine of 90 degrees minus theta. And finally, we learned that the co in cosine literally stands for complementary. As you step away from this explainer today, I want to leave you with this provocative thought. If something as seemingly distinct as sine and cosine are actually just perfect reflections of one another inside a 90-degree space, what other deeply interconnected secrets is mathematical geometry just waiting to show you? Thank you so much for hanging out and watching. Keep exploring, and I'll catch you in the next explainer.